In this video, we're going to look at number 1 from the 2019 AP Calculus test, AB form. It says a graphing calculator is required for these questions, which is good because we're going to get into some pretty hardcore math if we have to write it all by hand, and that would certainly take up more than a few minutes. Would take up more than 30 minutes just for this one question if we had to do it all by hand. Right, so in this question we're looking at maybe a fisheries problem. Fish enter a lake at a rate modeled by this function. We're starting with 20 fish at a time t0, which is midnight, and then for each hour that passes we get an additional 15 sine of pi t over 6 fish entering the lake. And then they're also leaving the lake. I don't know, are they dying? Are they entering by stream? I suppose if t is in hours and we're starting at midnight, then they're not dying at that rate, so they're entering and leaving by a stream or something like that. So we've got leaving is L of t, and we're then starting with 4 plus 2 to the 0.1 t squared. Okay, so our first question, how many fish enter the lake over the 5-hour period from midnight to 5 a.m.? And so what we need to do is find the integral from 0 to 5 of e of t. So I've got that already lined up here in Wolfram. Right, so we've got the integral from 0 to 5 of our function e of t here. I've changed t to x just because that's the standard variable. And we see that we have 153.46 fish. Now if we go down, here's a map of the function, a plot of the function. So we start at 20 fish at midnight, and then for each hour until about 3 a.m. we've got an increase in the number of fish. Around 3 a.m. now we've got an increase, still an increase in the total number of fish, but we've got a decrease in the rate at which they're increasing. So between midnight and 5 we have this many fish, which is 153.46 or 153 since we can't have 0.46 fish. Now if we had to do that integral by hand, you can see it would take quite a little bit of work. Some of it's fairly straightforward. We've got, we can integrate by parts. We've got a constant here. We're going to pull that constant out, right? And that one is quite simple. We're going to pull out this constant, but then we're going to have to do some u substitution here, and this is kind of a messy function. So we've got pi x over 6. We've got to substitute u equals pi x over 6, and then du, the derivative of that, of course, is pi over 6 dx. Then since we've got a constant on the outside and we're multiplying our integrand here by du, we have to take out the, we have to take 1 over du, multiply it by that constant, and go through a bunch of other steps. Again, luckily we have the use of a graphing calculator or Wolfram in the case of this PC demonstration. So we've got 153 fish entering the lake between midnight and 5 a.m. Letter B, what's the average number of fish to leave the lake per hour over the 5-hour period? So it's exactly the same thing. We're going to do an integral of our second function, which is a leaving function, 4 plus 2 to the 0.1 x squared. And we see that we've got 30.2952, but let's read that question a little bit closer. What's the average number of fish that leave the lake per hour? So we've got to divide that by 5 hours. Right, so our answer is going to be 30.2952 divided by 5. And we can use a calculator here. 30.2952 divided by 5 is 6.059 per hour, or 6 per hour, but we can leave the decimal in there since we're looking for an average per hour. Now Wolfram actually wouldn't even give me the step-by-step because it took too long, so I had to find another website. Oddly enough, this one is free, whereas Wolfram I had to pay. So we've got all the steps mapped out here. Again, it's really complex. So we start with changing the 0.1 to a fraction. We're going to do a little bit of integration by parts. That's fairly straightforward, like with the previous one. And then we do some u substitution. Again, we're starting to get into some more exotic math here, right? And here's where it really gets funky. When we have an imaginary error function, that's where it just exceeds the skill level and the practicality level for the average person. Even if your average person is in Calc 4 or something like that. Since we do have the technology and it's here to stay. We might as well let the machines do the hard work for us. In this case, the heavy lifting is done by a couple of different programs, and they come up with the same answer, which is good. Okay, so we've got, again, 30.2952 divided by 5, which is 6.059 fish per hour. And on to letter C. At what time T between midnight and 8 a.m. is the greatest number of fish in the lake? And so the real challenge of this problem, since we have technology available for the real heart, the mathematical processing, is just figuring out what techniques to use. Well, what does this mean? At what time is the number of fish in the lake the greatest? And so we've got fish entering the lake at this function, and then they're leaving the lake at this function, right? And so I want to know when does this function, when does the difference here become 0? I don't know, when does that become 0? If this were the graph here, when does that cross the x-axis there? So I've got that all plotted out here. I've got my difference of these two from 0 to 8. So again, we're starting with 20, just less than 20, because we've got right there at midnight, we've got roughly 5 fish leaving. And we've got the number of fish is increasing, 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 and then that rate starts to decrease at around 6 something here. That's the point where we have a 0, and so our maximum number of fish is right in there. So if we wanted to calculate that number, we could say solve this. For equals 0. And you can see even the technology takes quite a little bit of time, not nearly as long as it would for us to do this by hand. (6.2), right? So 6.2 hours after midnight. And so we can just phrase our answer in terms of t rather than having to put it into units on the clock, right? So 0.2 hours, we could calculate how many minutes that is and put it in terms of what time it is exactly, but t is equal to 6.203 hours after midnight. And that's the time when we have the greatest number of fish in the lake because, again, we had that function crosses the x-axis at that time. Final question, is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m.? We could go back. We'll go back and plot this one again. We could do this 2 different ways. The first way is just to look at the plot of the difference between these 2 functions, and we can see at 5 a.m. the rate is decreasing. We see the slope of that is decreasing. The other way to do this is to take the derivatives of each of these and figure out if the derivative of e of t, or e of 5, minus the derivative of L of 5 is greater than or less than or equal to 0, right? And so taking the derivatives of these equations, again, is really quite complex, right? We have to differentiate using the chain rule, using the power rule, of course. It's quite a few steps, so luckily we have the technology here to do all the heavy lifting for us, right? And so, easy enough. Calculus with technology. We can make short work of an otherwise really difficult problem. And so how many fish entered the lake? We had 153 fish entered the lake in that time period. What was the average number of fish in the lake to leave per hour during that period? We had 6.059 fish per hour. the greatest number of fish in the lake, somewhere around t equals 6.2. And is the rate of change in the number of fish increasing or decreasing? At 5 a.m. it is decreasing. And so there, in just about 10 minutes, we did what would have been 2-3 hours worth of work using technology.